Before you can go into too much detail about method of sections, method of joints, and all that kind of stuff, when we're talking about trusses, it's important to make sure you're aware of what a truss actually is. So to start off, oh, come here, silly computer. You're kind of going nuts over here. When we're talking about a truss, we are meaning we're talking about a structure of slender rods joined at their endpoints. So specifically just joined at their endpoints, and that's kind of what makes what we're going to do in a minute called method of joints actually possible. The second thing that we're going to also, well, the other thing we're really going to focus on really, how many times can I say really, are planar trusses. So for planar trusses, it just means a truss in a plane. So that means it's 2D, which is good because 2D is infinitely, well, not infinitely, one dimension easier than doing stuff in 3D. Now, in real life, trusses are going to be in 3D. So when we talk about a truss, we're usually going to mean something that looks, kind of like this, and it's like a truss, and it's a little bridge like that. Now, in real life, it's going to be three-dimensional, and that's fine. But what we can kind of assume is that you're going to have like floorboards here, and the people walking on the floorboards, that weight is going to be transferred to the joints, and then that the joints on both halves are going to be symmetric. So we can actually just look at these individual points, and basically, if we're getting started and what we're doing, if we're kind of making the initial assumption that this is okay, obviously I'm not going to go say, build a bridge for 80 million cars to go across every 20 minutes like this, but it's just kind of getting used to the idea of how structures work. So we're going to assume that this all kind of works in 2D. These are called stringers, by the way. So again, we assume that these forces are transmitted along the stringers and the floor beams to do, I guess these are the stringers and then those are the floor beams. But anyway, stringers and floor beams, that the forces are going to be transferred to the joints so that we can just kind of look at it that way. There are some additional assumptions that we're going to make. So this first one we already talked about, which is basically that all the loadings are going to be applied directly at the joints. So the idea of that is like if I have a truss, and I'm not going to think about, well, what happens if there's a weight here? That's not what I'm going to do. All the weights are going to be like directly here. So even if there's a dude standing here, that he's sitting on the floorboards and the stringers, so his weight actually gets transferred to these two equally. So even if we are looking at the beam and say, well, the beam itself has a weight, we assume that the weight of the beam actually, instead of being at the center, is going to be at the two ends. So that one has a weight here and 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 a weight here. So whatever those weights are, instead of having, something like this where we have, one weight in the middle, we're going to say, well, this one's weight over 2 and this one's weight over 2 and this is weight, I don't know, another weight. So weight 1 over 2 and weight 2 over 2. So it gets divided out. So that's really important, over 2 and weight 3 over 2. So instead of having single weights at the center, even if we're taking the weight of the beams into consideration, we are not looking at it like this. We're looking at it like this. So again, all the loadings are applied at the joint. So that's the big thing, the big first assumption that you want to make sure you have. And that's kind of funny because our second assumption is that we are usually actually going to neglect the weight of the beam. And that's because the load on the bridge is so much heavier than the bridge itself. So, I don't know if you're, well, and you see this like whenever you make like little bridges out of popsicle sticks, the popsicle sticks are super light, but then you put like 15 textbooks on it and you're like, oh, check it out. So the textbook weight is obviously a lot stronger or a lot heavier than the weight of the popsicle sticks. And that's the same thing that you have with bridges in real life, is generally that the bridge is not going to be nearly as weighty, or I guess, as the stuff that's going on it, especially whenever you factor into account like the wind loads and the snow loads and everything else loads. So that's important. Now, the third and the final assumption that we're going to make is that the members are joined by a smooth pin, which is funny because in reality, that's not how it works. So in reality, you're probably going to have something like a gusset plate. So you'll have all these things coming into here, and you'll have this like little, let me try drawing the plate first. So you have this like little plate that kind of comes in here, and you'll have these beams coming in here. I mean, we obviously don't make bridges anymore with rivets, but if you look at an old bridge, it's going to have just like tons and tons of rivets in here holding all this together. So in reality, you're going to have something, it's not just going to be, hey, check it out, it's all in a pin. But whenever we make our assumptions for the purposes, and again, that's because we just don't have the skills right now to do it more sophisticated. We're just assuming all of these are coming in at a single pin. Now what's funny is actually in reality, if everything's made of unobtainium and nothing bends and nothing breaks, we could theoretically make the bridge with a single bolt, but that is kind of scary and I probably wouldn't want to go across the bridge. So all these are sissy, they're for people who are afraid of, dying, feel like they have to have all these extra plates. But if you're tough, in reality, you only need the one pin. So you can turn that information about that one pin into what you need to do with the gusset plate. But again, this is statics. We're not actually building bridges. We're kind of learning the algebra of the rest of engineering. So we're just trying to pick up a little bit here. So we're going to assume that everything is pinned. This isn't really an assumption, but it's more of a convention. So I'll call this a convention. Is that, well, it's ish. Anything when we draw the arrows out like this is going to be considered in tension, right? Because you're pulling on the, you're pulling on the member of the bridge of the truss. And if you see the arrows coming in like this, we're going to call it compression. So that's not really the convention, but the convention is that whenever I'm drawing something, I'm always going to draw everything in tension. So the convention is that if you see something that's going to be positive, then we know that we drew it correctly, that it is in fact in tension. However, if we do a study and then we come out and we get like a -3, then that means it's got to be in compression. So if we originally drew everything in tension, then a negative number implies compression, and that just makes it a little bit easier to do that. And just in case you care, the tension in real life, we care if beams are in tension or compression, because these actually have to be thicker to prevent buckling, or reduce at least the risk of buckling. Buckling, not bucking. So tension beams can actually be thinner than compression beams. So that's just kind of a neat little thing. So these are kind of the basic assumptions and conventions that you need to do or need to know in order to do the method of joints and all that kind of stuff.